What can gravitational waves reveal about the vitality of our civilization? Their existence has been theoretical since 1915. Now we have LIGO, a $1.4 billion detector built for one purpose: to turn theory into fact. Its precision challenges the laws of physics, yet it shares heritage with technology that is centuries old. Together, we will learn how LIGO works and what that implies for scientific advancement. What we perceive as gravity is really the curvature of space-time by massive objects. The Earth follows the curvature created by the Sun, and we are firmly rooted by Earth's curvature. The theory predicts that these curves are not fixed. Objects come and go, creating new curves in space-time. The general theory of relativity predicted that if very massive objects quickly change, relatively, then they create waves, not unlike a pebble being dropped into a pond. Many scientists over the years endeavored to come up with a way to detect the waves. The technology just did not exist to test this aspect of Einstein's theory. Well, that's not quite true. An important piece of the answer to this question had been around for over 300 years. The thinking was that gravitational waves would affect the very fabric of reality and anything moving through it. So experimentalists turned to a very well understood branch of physics that had a long history of results. And that would be this: optics, or the telescope. Invented by Hans Lippershey in 1608, it used curved transparent glass and mirrors to manipulate light in order to acquire information about distant objects. The main problem with trying to detect gravitational waves is that the measurable influence that they would have would be very, very small, about the size of a single atom compared to the distance from the sun to the earth. Optical technology would improve greatly over the centuries to come. However, direct imaging of a gravitational wave with a telescope would not be the way to turn theory into fact. The next critical piece would not arrive until 1960 in the form of a laser. The stage was now set to try and listen to the universe. In 2002, engineers put together lenses, mirrors, and lasers to create the Laser Interferometer Gravitational Wave Observatory, or LIGO. Using two 4-kilometer-long arms, LIGO generates a single laser beam that is split, then sent down separate but identical paths. They are then recombined when they return. If one light path has been affected, then they will create an interference pattern when they are recombined. The idea is that gravitational waves will very slightly alter the distance one of the beams travels, about 4 times 10 to the negative 18 meters, or 1/1000th the diameter of a proton. This is still enough of a distance to, maybe, be detectable. As you can imagine, isolating the experiment from outside noise is very important. LIGO's instruments are suspended from pendulums, kept in a vacuum, and humans need to keep at least 5 meters away, as their bodies could produce noticeable gravitational effects. LIGO is the National Science Foundation's largest project to date. Not only is it cutting-edge technology, but they built 2 identical detectors, one in Louisiana and one in the state of Washington. With this arrangement, they would be able to confirm findings and give some direction as to where the signal originated. Remember, the goal is to detect the after effects of stellar phenomena. Much like a seismometer detects waves in the Earth, the hope is that LIGO could detect waves moving through space-time. How they arrive may be able to tell us new things about how the universe works and open a new frontier of exploration. All studies of the cosmos so far have been using the electromagnetic spectrum. This would open multi-messenger astronomy, the ability to reinforce or alert one mode of detection with the other. From 2002 to 2010, LIGO did several observation runs. Data was collected and analyzed by scientists from all over the world, and they found nothing. No gravitational waves at all. Over the next 5 years, major updates were made to increase the sensitivity by 3 times. On September 12, 2015, LIGO was restarted. Would the time, money, and effort be worth it? Science did not have to wait long to find out. Just 2 days later, they made their first detection. Since then, LIGO has made over 90 detections, with one in 2017 being of significant importance. It was the first time multi-messenger astronomy was used. The gravitational wave LIGO detected was immediately reported to the world's observatories, and they were able to capture the merger of 2 neutron stars. Even the Hubble Space Telescope got in on the action. Over 160 institutions have worked on this data over the years, including 440,000 people using their personal computers to run Einstein at home. Proud study at home user right here, reinforcing that interconnected nature of scientific progress and shared knowledge. This is how we take steps into the unknown. By standing firmly on proven facts, we test the theory. The result, positive or negative, doesn't really matter, because no matter which way it goes, you learn something that you didn't before, don't you? Massive celestial bodies can create gravitational waves that are detectable millions of light years away. After 89 years, this theory became fact. A solid place to stand on to further our exploration. So solid, in fact, plans for larger and more sensitive gravitational wave observatories are underway. The Cosmic Explorer in the United States, the Einstein telescope in Europe, and LISA, a space-based laser interferometer, all to be operational in 2035 or so. What else can be heard in these waves? Can they reveal cosmic structure? Can they be made to serve us? There is no expiration date on scientific knowledge. In this case, optical technology from the 1600s was used to test the theory from 1916, which was possible because of lasers from 1960 and the computers of today. What pieces of past naturalistic inquiry will become relevant in the years and centuries to come? Certainly the algorithm is having a moment. First derived around 300 BC, Euclid's algorithm is still being used in computer software today. Chances are you're using it right now. Once we have that stable platform to stand upon, our ability to see expands. Check out the next episode for the frontier. In this way, we build the scaffolding of civilization. The path is not always clear, and unexpected results can move humanity more than expected ones. We got penicillin from an accidental discovery of mold-killing bacteria in a petri dish. Plastics came from a chemist trying to make a better shellac by heating coal tar. We are efficient with our knowledge. Let none go to waste, and in general, gleefully share what is found. It is innate in us. Without the step of solidifying knowledge, basic research would sit unused on shelves or in scrolls until the end of time, but that is not our way. We continually desire to see beyond the veil just a bit more, and with each peak, we enrich our civilization and lay the seeds for our continued success. To help Aletheion continue to explore, please like and subscribe. We also have a Patreon for those that are inclined, and if you'd like to add to the discussion, please join the Discord. Links below.